Ms. Ferrari, are you having questions for the homework? Okay.
I'm sorry, did you get another file? It is. No, I'm not.
All right, so yesterday we did the Wilcoxon matched pairs 2 sample tests. So between the Wilcoxon and the Mann-Whitney, when I've done my research on this, I've seen these 2 tests kind of used interchangeably. I've definitely seen them named interchangeably. The big difference is one of the tests is a matched pair. That's what we did yesterday. They have to have the same end size. Okay, so whatever you want to call it. What we did yesterday was the procedure for a matched pair. Okay, this is going to be the procedure when it literally is just 2 separate samples, not necessarily a matched pair, which means you don't have to have the same end size. The one we did yesterday, literally all the values had to line up. Okay, and then we subtracted them to kind of get that new column. Now, in this first example that I did, I purposely chose, look, just a little n size of 4 and a little n size of 3 to really reinforce you don't have to have the same n size. But then most of the 3 examples we're going to do, they just all happen to, okay? So the Mann-Whitney test was developed back in 1947. And it is used to test the equality of 2 population medians from independent samples. The idea is to combine the 2 samples and then you rank them. Okay. When you think back to the null hypothesis, which is typically, however you phrase it, what they usually mean is there's no difference. Okay, so kind of the concept is if there's no difference, why wouldn't we just lump them all together? Okay. So that's what we start with. We take all of these values and we put them all together in order from smallest to largest and we rank them. 1, 2, all right, now both of these are an 8, so 1 would be a 3 and 1 would be a 4, but how do we know which is which? And we don't, so we just say, well, what's the average of 3 and 4? 3.5, so they both get a 3.5. But 1, 2, 3, 4, 5, 6, 7. And then what you do is you go back and you find the rankings that correspond to your first data set. So you would go back and say, okay, I need this one, I need this one, I need the 10, and I need the 13. And you get what's called S by adding up those rankings. And you get 18.5 when you add those all up, okay? So then that S value is used to calculate the test statistic, which is called T. So in order to do the test statistic for T, for the small sample case, you take that S value that we just got, which was 18.5, and you would subtract, all right, now it says n sub 1 and then times n sub 1 plus 1. You now go back to your data and you say, okay, the first set of data, call that data set 1. So n sub 1 was 4 here, and n sub 2 was 3. So we're only going to use the value of 4. So we would then do 4 times 5 and divide that by 2. So in this instance, 18.5 minus 10, you would have a test statistic of 8.5. Okay? And like the last couple, I'm not going to go through the derivations on all these things. Okay? My whole idea of doing this is just to introduce you to these non-parametrics so that if you end up in a stat course someday or a course that applies these, you are like totally lost and at sea. You kind of like, oh, I remember hearing about that. So here are your tests. You can do a left, a right, or two-tailed again. And the M is the median of the various populations. Okay, for small samples, if you do a left tail test, you will be checking to see if your test statistic is smaller than the critical value you read off the chart. For a right tail test, you're going to reject if T is greater than the critical value, which is kind of off the chart. I'll show you. And then for a two-tailed test, you're going to have two critical values, a low and an upper, a lower and an upper, and you're going to reject if your test statistic is lower than the lower critical value, or if it's greater than the greater critical value. And you only use half of alpha for that. Okay? Lots of little things to remember on these. And that's what, the first day I presented this, I said that one of the things that some researchers or statisticians will do is they will use these non-parametrics when they really should be doing the real thing, because these are considered easier. To be honest, I find all these little details, they make them a little bit more complicated sometimes, because here's your critical values. All right, if you're doing a left tail test, you literally, this will be what you read right off of, I think we're on table 12 now. So for the left tail test, it's easy. You grab the number off the table like we've been doing for the past couple days. But for a right tail test, you use that number, but you subtract it from the product of the two n sizes. And for a two-tail test, you do both of these, but you use half of alpha. So you read from a different row in the table. Okay, so, and this is why I actually have 3 examples today, because I want to do one of each. I want to do a right, a left, and a two-tail, okay? Once again, I'm going to skip the large sample. We're just getting close enough to the end here. I don't want to overwhelm you guys. So I'm just trying to introduce these. This is what the large sample would look like, but you'll notice I put a big X by it. You don't need to know this. It's just there so you see it. Okay, so here we go. Small sample situation. When exposed to infection, a person typically develops antibodies. The level of response can be measured by looking at a person's titer. I had never even heard of that word. Did you? I hadn't. I had to look it up for the pronunciation and the definition. But yeah, basically it measures the level of antibodies you have in your system. And if you have a high level antibodies, it indicates that you must have some sort of an infection that your body is trying to eliminate. All right, so a higher titer means more antibodies. The data in the table represent the titer levels of 11 ill people. And that's actually what that says. It looks like Roman numeral 3, but it actually says ill. And then there are 11 healthy people. All right, so this will be N1, which would be 11, and this would be N2, which just happens to also be 11. For this test, those do not have to be the same N sizes. They just happen to be. All right. So these people were all exposed to a virus in Vermont. Test the claim that the level in the ill group is greater than the level in the healthy group. Okay, so there's your null hypothesis. The median level of the ill group is greater than the median level of the healthy group. That's the alternative hypothesis. The null, of course, is always that things are equal. Again, that's how we write it mathematically, but what we're saying then is if the medians are equal, we're saying there's no difference. That's an H, believe it or not. Okay, we're saying there's no difference. Oh, and M, I'll call it M sub I equals the true median titer level in both ill and healthy people. Okay, so there's my hypotheses, my definition. All right, so how you rank things is going to be up to you. But one of the things that I showed my third hour yesterday, I don't think I did it with you guys, is one way to do this is I'm just going to enter all of these numbers together in one column. Because remember, the null hypothesis is that there's no difference. So I'm just going to lump them together. So I'm just going to put all these numbers in my calculator. Shouldn't take me too long. And if All right, 640. I hope I don't make a mistake since I'm typing super fast. If you're not typing in any ways, if you're just watching me, you're welcome to stop me if I make a stupid mistake. 320, a couple more 320s, an 80, a 160, a 10, a 640. I think I got them all. Okay, so there's different ways that you can, when you want to rank these, okay, it's not like it's hard to rank, but this is just one way to kind of do it. All right, if you look at my work on my paper, it's really messy. But when I often do it by hand, I literally combine data. I have all the numbers. I literally went through here and you can see the little dash marks. Those aren't negatives. That was just me marking like, okay, yep, got it, 10. Got it, 10. Okay, because I want to make sure I didn't miss anything. I generally like to do it like this because I like to see it. I like to see it ranked. But where the calculator can help you is I'm going to go into stat and I'm going to sort. I'm going to sort by ascending, and I want to sort L1. And Inspires, you have a sort option also, and it says done. And now when I go back in and look at my data, it put it all in order for me. And that's actually probably maybe that's sometimes what I do, and sometimes I still copy it down on my paper so I have it. But this allows me to have it in order, and then I can rank it more easily. So I'm going to copy these down. All right, it's going to be very squishy here because, no, I'm not even, I'll run out of room if I do that, okay? We'll go with this. So when you rank these, when they're in order, so there are 2 10s, so that would have been 1 and 2, and you're like, but I don't know which one should be 1 and which should be 2, so we call them each 1.5. And then there were 2 80s, 3 and 4, so I call them both 3.5. Okay, so 1, 2, 3, 4. All right, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. And what would be the mean of 5, 6, 7, 8, 9? 7. And that's why they all got 7s. Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I averaged those rankings and I gave them all 12.5. 16, 17, 18, 19, 20. I averaged and gave them all 18. 21, 22, I averaged those and gave them 21.5 apiece. That's the reason I like to actually list it on my paper so that I can see how many are being repeated. And I can literally, and sometimes what I do is I will literally write down like this. I'll go 1, 2, 3, 4, 5, 6. I really do list them all the way down. So then I can say, okay, since these guys are all the 160s, I literally can figure out what's the mean of all those numbers. And then I'm like 10, 11, 12, 13, 14, 15. Okay, I need to figure out the mean of all of those numbers. For me, it helps to put it on my paper, okay? But then when you notice this, I have some of these circled. Why are they circled? Because at this point, once they're all ranked, now you go back and you say, well, I only want the ones that are in group 1. Okay, now how do you know which one is group 1 and group 2? It was how we defined it over here. I said M sub I was greater than M sub H. So M sub I kind of defined as my group 1. So I went through and said, okay, group 1 had a 640. I went and circled that. Group 1 had an 80. I circled that. Group 1 had a 1280. I circled that. And I went through and I circled all the values that went with the ill people. And when I did that, I added up all their rankings and I got an S of 152. That is the sum of the ill people's rankings. after combining. Okay, so you combine them all, you rank them, but then you go back and say, but now I only want the ones that came from group 1. Now understand, you could do this test in reverse. We could have set this up as M sub H is less than M sub I, in which case we could define M sub H as group 1, and then we would use all of theirs. But this is how I defined it. All right, so S is used to calculate your test statistic. So your test statistic is, and you're going to have a formula page, S minus the n size of group 1, which was 11, times that n size increased by 1, and that gets divided by 2. So that would be 11 times 6, or 66. So 152 minus 66, I have as 86. That is your test statistic. Now we are going to be doing a right tail test. So eventually we're going to have to say, is T greater than our critical value? So what is our critical value? Well, for a greater than right tail test, you're going to read the value from table 12, but that will get subtracted from the product of the two n sizes. So the product of the two n sizes would be 11 times 11 minus, all right, now this number is going to come from table 12 right here. All right, so table 12, and it's labeled table 12 Mann-Whitney. You're going to be on the second page of the table because we have n sizes across the top. We have n sizes down the side. So we have both our 11. So I need to be in this column. And we are doing a 10% level of significance, which gives us a 41. So this is 121 minus 41, which is 80. That's your critical value. So is 86 greater than 80? Yes, so we will reject the null hypothesis, and we could make our formal conclusion that we do in fact have sufficient evidence to reject the claim that there's no difference between the titer level in the ill versus the healthy people in favor of antibodies are more highly present in the people who are sick. So that's the right tail test. The left tail test. Suppose researchers are trying to compare weights of packages from two different distributors. At the level of significance of 5%, is there evidence to support the claim that the weights from population A are less than those from population B? So the null hypothesis is that the median weight from A is equal to the median weight from B, and the alternative hypothesis will be that the median from A is less than the median from B. And M sub I is the true median weights of packages from the distributors A and B. All right. So if I put these in order, okay, one of the things you could do also is I sometimes, now you gotta be careful on this because you mess one up and you're gonna totally, then you have to go back and recount. But you could do this, you could say, okay, this is clearly the smallest one, so I'm gonna give him a 1. Okay, so who's the next smallest one? 38.9. And then 48.4, 48.5, 48.8, 60, and then 61.2, and then 61.3, 62.4. All right, but now there are two 63.4s. So I would want those to be 10 and 11, so I'll just call them both 10.5. So 10, 11, so 12 is going to go to this guy, and then 13 goes to 67.3, 14 goes to 67.8. Now there's two 73.3, so that would be 15 and 16, so we'll call them both 15.5, and then 17 and 18. Now, if you're watching me, you'll notice I'm literally copying down because I already did it here. You can do it this way, but again, you got to be really careful because sometimes when I've done that, I get all the way through and I realize I missed one. Like I said, there were two 73.3s. What if you didn't notice that right away? Now you've got them all numbered. You're like, now you got to go back again, okay? For me, I find it safest. I type them in my calculator in one column. I sort it. I copy that on my paper. I rank it. And then I go back and circle the ones I want. The benefit of doing it this way is I don't have to go back and circle the ones I want now. I know that I want all of these. I want all the rankings from the first group. So I add those up, and that is my S, which here is 60. So my test statistic is that S value minus the N size of that group, which was 9, times the N size increased by 1. Always divide that by 2. So that's 90 divided by 2, which is 45. 60 minus 45 gives me 15. Now this is a left tail test. So I want to test, is my test statistic going to be smaller than my critical value? Well, what is my critical value? For a left tail test, the good news is you just read the table. Literally, you just go to table 12. All right, so I have two N sizes of 9, so I'm going back to page 1. I'm doing a 5% level of significance. So I'm going to get a critical value of, I see a 22. So is 15 smaller than 22? Of course it is. So we're going to reject the null hypothesis and you'd make your formal conclusion. And then one more quick example so you can see how the two-tailed test works. The effectiveness of advertising for two rival products was being compared, brand X, brand Y. Market research at a local shopping center was carried out with participants being shown ads for two rival brands of coffee, which they then rated on their overall likelihood of them buying the product. Out of 10, with 10 being, I will definitely buy the product. Half the participants gave ratings for one of the products, the other half gave ratings for the other. 5% level of significance. Is there evidence to support the claim that one brand of advertising is better or more effective than the other? Don't let the phrase more effective confuse you. That might make you think greater than. But this is not saying that one is definitely greater than the other. We're just saying which one. This is going to be a null hypothesis of there's no difference versus there is a difference. They're just not equal. M sub I is the true median ranking for brands X and Y. Now, definitely, when you have such a small set of data here, you totally can just do this right here. You're like, all right, the smallest one is 2, but there's 2 of them. So that has to be 1 and 2. So I'm going to call them both 1.5. So 1, 2, 3, 4, Okay, there's 2 5s. So there we go, 5 and 6. So I'll call them both 5.5. 5, 6. 2 6s. So they'd be 7 and 8. So I'll call them 7.5. 7, 8, 9, 10, 11, 12. But we only want these rankings now. We add those up, and that adds up to 23. And our test statistic is that S minus 1, 2, 3, 4, 5, 6 is our N size. Multiply by, increase that by 1. Always divide by 2. 23 minus 21 makes 2. Now, your critical values. This was an alpha of 0.05, but because it's a two-tailed test, you are going to look at the row for 0.025. Okay, you're still going to do the same N sizes of 6 and 6, but you're going to read a different row, and you're going to get 2 critical values. You are going to take one of them and literally just read the number like you did on the left tail test. And then you're going to do one where you multiply the 2 N sizes and subtract that number. So let's see, what do I get if I just read the number? N size 6. N size 6 puts me in this column, but I want 0.025, so I'm seeing a 6 off my table. And then the other one, multiply the 2 N sizes, so 6 by 6 gives me 36. Subtract what you read from the table to get 30, and there's your lower critical value, and there's your upper critical value. So now you have 2 things to test. Is T smaller than the lower critical value, or is T greater than the upper critical value? And in this case, 2 is smaller than 6. So we are going to reject the null hypothesis, and we would make our formal conclusion. Now, just even looking at the data sets, okay, all we conclude now is that there is a difference. Now, what's my hunch? It sure looks like that the median ratings for brand X are, lower. And that would be why the lower critical value is the one that, tagged us. But that's the Mann-Whitney test. Now on Monday, I'm going to introduce one more test, but we're not doing notes on it. I'm going to introduce it through just an exercise that we'll do in class. It won't be on the test. Tuesday and Wednesday, you guys can work on, there's a review worksheet in your packet, and I'm going to be gone on Wednesday, the day before your test, just so you know, okay? So then on Thursday, you'll take your last test, no multiple choice. You'll have a formula page, okay? It really shouldn't be too bad. You'll have the table packet, the formula page, and then on Friday next week, you guys know it's a half day, right? Okay, so it's a 3-4 half day. You guys will probably be getting here a little bit. I think you guys get here sometimes a little bit late because of the buses, but if you guys drive, you guys will be okay, whatever. But you guys will be going to Ms. Garmo's room because we're going to be running a senior breakfast in here, okay? We're going to open the wall and we're going to run a senior breakfast. So you guys are going to go to Garmo's room, but I will very likely come down to Garmo's room and introduce, I told you guys you're going to do a little project to end the school year. So my plan is next Friday to introduce that project. If something happens, I don't get down there, well, then I'll do it, when we get back from the long weekend. But that's our agenda. That's it. We're getting close, people. Yes, sir. I would give you anything you need. Yeah. We'll talk more about that, though. I'm still I admit, what I'm debating also is, I'm debating between creating formula page for you and just letting you use your notes, just doing an open note. I mean, that's what I'm debating about. That's what I'm debating on. So